So we had introduced the idea that if force and the displacement are not in the same direction, then the only component of work that matters, only component of the force that matters is the component that's parallel to the x. Okay, and so we would say that the work is going to be force times the displacement times cosine of the angle theta. And so that introduces us to the vector nature of this. So in other words, if you are pulling a wagon, okay, you got friction here, and you're pulling the wagon along like this, and the force is an angle like that, and this is some angle here, so this is 25 degrees, then if you pull this so that it goes a distance of 1.5 meters, and the force was 30 newtons, then obviously the work, okay, well, the work is normally force times distance, so you'd think that would be 45 joules. Well, it's not, okay, because only the component of the force in the direction of motion matters. So that means it's going to be fx cosine theta. And so that'll be 30 times 1.5 times cosine 25 degrees. So that comes out to be only 40.8 joules of work that you did. Okay, now that's the work that you don't have, and it turns out there's friction involved. Friction is doing negative work, but we'll get back to that later. And so, so now we have this vector. So this introduces the idea to the vector dot product. We have a vector A, okay, and then we have vector B, and there's some angle between them. Now, in math, we learned that there's something that comes about from A dot B. A dot B is going to be a scalar. The scalar is going to be magnitude of A times magnitude of B times cosine of the angle between. Okay, so I'll let the math faculty go through the details of that. But in physics, we're concerned about it primarily here as terms of how it relates here to what we're trying to do for this particular case. So we're just going to take a math interlude back to chapter 3 of the textbook for just a moment. Because I skipped the vector dot products when I did that before, because I knew I'd get back to it later. So let's consider A dot B. Okay, so what is A dot B? Okay, A dot B is going to be vector A, that's AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK. That's AX, BX, I dot I. Y'all know how to do this, right? This is just multiplying two polynomials. Plus AX, BY, I dot J, plus AX, BZ, I dot K, plus AY, BX, I dot J, plus AY, BY, J dot J, plus AY, BZ, J dot K, plus AZ, BX, K dot I, plus AZ, BY, K dot J, plus AZ, BZ, K dot K. Now that looks kind of complicated, but it turns out things get simplified very easy. So if we have I dot I, now what is that? That's going to be equal to magnitude of the unit vector is 1 times 1 times the cosine of 0 degrees, which is also 1. So that's just 1. So that means that this is just 1. Means this right here is also just 1. This right here is just also just 1. Well, what is I dot j? That's going to be 1 times the cosine of 90 degrees, because I and j are 90 degrees apart. That's 0. In fact, anytime the two vectors are 90 degrees apart, then the dot product is 0. So that means this term goes away. Well, wait a minute, the next term is I dot k. They're also perpendicular to each other, so that goes away. Next term's I dot j, that goes away, okay? And then we have j dot k, that's perpendicular, it goes away. We have k dot I, that goes away. K dot j goes away. And so all that we have left, a dot b, is ax bx plus ay by plus az bz. So now we have, well, this is actually now simple. We have two vectors, and we got a force vector, we have a displacement vector here, there's some angle apart. If I'm giving these vectors to you in vector format, and unit vector format or component format, then you just multiply the x parts together, add that to the y parts multiplied together, and add that to the z parts multiplied together. And that makes this actually very simple. So, for example, I could have a force vector, and say the force vector is going to be 4.21 newtons I plus 4.45 newtons J plus 1.15 newtons K. And let's say that we have an x vector, the displacement vector, and so let's say that the x vector is going to be equal to 1.05 meters I and 3.66 meters J and a negative 1.21 meters K. And so I want to know what is the work done by this force. Well, that's simple. That's going to be just F dot X. So what is F dot X? That's going to be 4.21 newtons times the 1.05 meters plus the 4.45 newtons times the 3.66 meters plus the 1.15 newtons times a negative 1.21 meters. And so the work done is 19.3 joules. So that makes it very straightforward. If you know F in the component form and X in component form, this is how you would find the amount of work done by that force. Now let me ask you another question. What's the angle between F and X? Okay, because this is complicated because F is in 3 dimensions, X is in 3 dimensions, and I want to know what's the angle between the two. Okay, now the problem is the angle is not in the XY plane. The angle is not in the XZ plane. The angle is not in the YZ plane. The angle is in 3 dimensions right there. So that makes it very complicated to find that angle. Well, no, it's not really complicated, because what we can do is we can look at this and say, oh, wait, we know that work is F times X times cosine of the angle. Well, F is the magnitude of the F vector. So that would be the square root of 4.21 newtons squared plus 4.45 newtons squared plus 1.15 newtons squared. Basically, this is the Pythagorean theorem in 3 dimensions. So that comes out to be 6.23 newtons. The x is going to be the magnitude of the displacement vector. So that is going to be 1.05 meters squared plus 3.66 meter squared plus 1.21 meters squared. That comes out to be 3.94 meters. Okay, so by using this relationship up here, then I could then say that cosine theta equals work over fx. Okay, all right. So that means theta is going to be the inverse cosine work over fx. So theta will be the inverse cosine of 9.3 joules divided by 6.23 newtons, 3.94 meters. Okay, and so that comes out to be 38.2 degrees. Okay, so anytime you have this vector vector dot product, then what happens is you can now utilize it if you know the result of the vector dot product and you know what the other vectors are, then you can work backwards to figure out, well, what was the angle between the two vectors. So I did this for work of force and displacement, but this would work for any application where you have the vector dot products. So once again, you can work backwards. You know, if you've not yet taken Calculus 3, then when you take Cal 3, there'll be a section of it that's dealing with these vectors, and this is one of the common questions they ask is, well, what's the angle between these two vectors? Well, what you do is you do the vector dot product, and then you know from there you can figure out the angle between the two. I should point out that all this work stuff, this is chapter 7, okay? The vector dot products, that is chapter 3, okay? And that's why the homework for chapter 7 has also some chapter 3 homework problems in it. And that's because to really understand the work, we have to go back and do vector dot products. I skipped the dot products when we were doing that in chapter 3 because I knew that we'd be getting back to it later. And rather than covering it and letting you forget, I thought it'd be easier to cover it as we need it. Generally, I've heard a lot of people find that mathematics is easier when you're covering it as you need it and you see exactly what it's being used for at that point than if you cover it and then long time passes before you end up using it.